Today we're going to continue talking about BigO. We're also going to talk about big omega and big theta. We're going to continue doing some induction with inequalities. And I'll talk about the test just a little bit also. We have test 2 coming up next week. And you have homework 6 due today. It's lecture 14 today. We have 27 lectures total, so we're about halfway through. So that might make you feel good or not, I don't know. So let's go ahead and get started. Are there any questions right now before I start? No questions.
Cheat method.
The cheat method? The cheat method for recursion, okay. I call this the cheat method because it always works and it doesn't require you finding a pattern in the closed form that you've seen. So for example, if I have something like a sub n is n squared minus n, and I need to find a recursive formula, then I would do, the cheat method is this. You use the formula to find the previous term. Then you subtract the 2 equations, the left-hand sides and the right-hand sides. So you get an minus 1 equals whatever the stuff is on the right. So in this case, we got n squared minus n minus 1 squared plus n minus 1. You don't even have to solve this down. Just solve for an. And this is a recursive formula, except it's missing something. What is it missing?
Basis.
It's missing a basis. We can't have a recursive definition without a basis. So our basis is what? A sub 0 or 1 is fine. So a sub 0 equals, and what does it equal? 0 squared minus 0, which is 0. So this is my answer, and that's the cheat method. So I didn't even do any algebra at that point. I just did some subtraction.
I didn't catch how you did that.
You didn't catch how I did it. Okay.
I see
this step is the definition of the formula.
Right.
I plugged in n minus 1 into the formula.
Okay.
Because a sub n is a function. N is the variable in the function. If I put a sub n minus 1, then everywhere I have an n, I put an n minus 1.
Okay, so that was your first step.
That was my first step. And then I subtract the equations. Just like when you're solving 2 equations for some unknowns, you could subtract the left-hand sides and subtract the right-hand sides, and you still have an equation.
I just don't see where the a to the n minus a to the n minus 1 comes from.
Subtract the left-hand sides. A sub n minus a sub n minus 1 goes to the left. And then all of this stuff minus that goes on the right. Here, how about this? A equals B, C equals D.
No, I just didn't see it.
Hang on. If I subtract the left-hand sides, I get A minus C. Subtract the right-hand sides, I get B minus D. Do you believe this equal sign?
Okay, I see.
That's
what
exactly what I did here. I put a minus there, a minus here,
Okay, so you're using
and then I add these.
the first, the given equation, and then your n minus 1 equation.
Right, I'm using both of them together. Because what I need is a sub n in terms of a previous term. So what I did is I used the formula to make up a previous term, and then I subtracted them. And then I solved for a sub n. That's why it's called the cheat method, because it doesn't require me to understand this recursion or formula at all. So if you really want to, this will get you a quick answer, and it's going to work all the time. If you really want to understand a function, you should also make a table and try to see if you can see the pattern that you get this way, or some other pattern.
And then how did you come up with the basis equal to a sub 0?
I use the formula again. I can't find anything without the formula. So if I put in a 0 for n, that's equal to what?
0 minus 0.
Right.
0 squared minus 0, which is 0. That's how we did it. So we're using the formula 3 times. We use it for n, we use it for n minus 1, and we use it for 0.
So are you trying to get 0? Is that?
Yeah, that's what I was trying. I had to get a basis. I used 0 for the basis.
But you
Whatever
could-
the value ended up being is what the answer would be. A sub 0 would be whatever that value is.
Yeah, so I
Then
wasn't trying to get
sub
0 on the
into
right-hand side.
formula.
Oh, you just always plug in ace. Okay.
I plug in whatever this number is. So if I wanted to get a basis of A1, I would plug in 1. I'd get 1 squared minus 1 happens
Right,
to be
okay.
0 also.
I just don't know where. I mean, I guess I'm having trouble seeing why you pick 0 instead of 1 or 2.
It doesn't matter what value you pick as long as you pick one and have a basis.
Okay.
I could pick 1,000 as a basis.
Okay.
I don't care as long as I have a basis. When you want to prove something recursively, you have to have a basis and a recursive rule. No one says like what the value of the basis has to be.
Okay.
Okay, I have an undefined function if I don't give you a of 0, right?
Mm-hmm.
That's fine. So just pick a basis. It's all right. Whatever you pick is fine. So that was the cheat method for recursion. So maybe we need to talk about recursion just a little bit more before we do some more Big O. So let me do a little review. When we have, if I have a linear homogeneous equation, is that good for me to do? All right, good. If I have a linear homogeneous equation, then that means I have some formula for S with some constants multiplied by S's. Let me make this so I'll actually be able to factor it. So let's see. That 4 would work. That's just like your homework, right? But I'll make a different basis. So whatever the basis was, I hope I won't put it. Let's put 0 and 5.
14.
Okay, so what I want to do is find the characteristic equation first. So what is the characteristic equation?
A to the n equals C.
I'm going to skip some steps, okay? Because once you've been doing this a few times, you're going to skip steps too.
X squared
So
minus.
this one ends up being x squared, right? I copy the 4 down, the x goes with the n minus 1 term, and a 1 goes with the last term. So it's going to be x squared equals 4x minus 4. You don't have to do all those other steps because it always comes out the same way, right? I always get, if I have 2 terms, I always get x squared and an x term for the n minus 1 term and a 1 term for the other term. So you can just go ahead and write the characteristic equation right when you get started. And then I just solve this for 0. Then I use the quadratic formula or factoring. This happens to be, what, x minus 2 squared, right?
Yeah.
So I don't even have to use the quadratic formula for that. So I have 2 roots. So what do I do if I have 2 roots?
You put in
Solve
an
for
n.
1.
C1
Yeah.
R
You
to
add
the
an
N.
I have to say that
C2.
if I want to get
Yeah.
a formula that has, since it's just one root, I have to have an n in the second one. And the reason why I do is because if I didn't, just suppose I put C1 R1 to the n plus C2 R1 to the n. I could factor out an R1 to the n, and that would be C1 plus C2, which is really just a constant. So I really didn't change it to something that should have 2 roots. So if I have 2 roots, I have to make it so that those constants can't add together. And the easiest way to do that is to multiply one of them by n. That's a method that we use in math, and if you take some more calculus, you'll be doing that when you do derivatives and things. If you want to make things linearly independent, you multiply one of them by x or n or whatever your variable is, and that will make them independent. That means you can't combine them like this. So if I have an n, I can't just combine these and get a new constant. That's what makes them independent. So after I do that, my root was 2, so now I know that Sn is equal to C1 times 2 to the n plus C2 times n times 2 to the n. That's also equal to 2 to the n. I'm factoring out the 2 to the n because it's a little easier to see the formula this way. So I need to find what C1, the next step is to find C1 and C2. And I have to use the basis for that. I have S of 0 equals 0 and S of 1 equals 5. And I'm going to use those two in this closed form to find them. So that means that this S of 0 is going to be 2 to the 0 times C1 plus C2 times 0. And S of 1 equals 5, which is going to be 2 times, obviously I'm going to have a fraction in here. It's going to be C1 plus, yes, 2 to the 5. Thank you. No, 2 to the 1. Don't mess me up like that.
Sorry.
2 to the 1. It was 2.
We're just testing.
Okay. All right, so it's 0 equals C1, and 5 equals 2 times C1 was 0, so this is just C2. So C2 is equal to 2.5. C1 was 0, so in my formula, I'm just going to have S of n is equal to, I'm just going to be plugging in right here. So S of n is equal to 2 to the n times 2.5 times n. So even though C0 ended up being 0, this ended up leaving an n in the recursive formula. So that's the reason why the n is there is because it was a double root. One of the constants happened to be 0. It doesn't matter that it's 0. This will hopefully work out as the right recursion. And how can you see if that works out?
Proof by induction.
You can do a proof by induction, right? You can make a table to verify it to yourself, and then you can do a proof by induction to really prove it. So that's going to be the next thing we do, just to remind everybody how to do proof by induction for a recursion. What's the first part? So I do a basis. And how many things do I need in my basis?
So 2, I guess.
I need 2, because my recursive definition has 2 terms in it, has 2 things in the basis. So however many things I have in my basis, that's how many basis points I have to have in my proof, and that's how many assumed steps I have to have. So here I need to have S of 0 and S of 1. You should be able to do this on automatic. So S of 0 needs to have 1. That's 2 to the 0 times 2.5n. n is 0. So that's equal to 0. 2 to the 1 times 2.5 times 1 is 5. So those two work out. Then I need to make an assumed step that has 2 points in it. And what it needs to have is the 2 things that were in my recursion definition. I need to have an assumed step for Sn minus 1 and an assumed step for Sn minus 2. Both of those need to be written in closed form. So I write them in closed form. So Sn minus 1 is equal to 2 to the n minus 1 times 2.5 times n minus 1. Sn minus 2 is 2 to the n minus 2 times 2.5 times n minus 2. And I need to prove the closed form for Sn. So these 2 things were on the right-hand side of my recursion, Sn minus 1 and Sn minus 2, and Sn was on the left-hand side.
What's the basis of S of 0? It's 2 to the 0 times 2.5
2.5 times 0.
times 0.
Right. So this is my setup here. Now I start with the recursive definition, which is S of n equals 4s of n minus 1 minus 4s of n minus 2. That's what I start with. And then I plug in the closed forms from the assume statement. That's why we set up the assume and prove the way we do. We set them up that way so that we can actually plug in the closed forms in the recursive statement. Okay? I see some sleeping and some confusion. Anybody got any questions?
Yeah. Yeah.
You have a question?
Yeah, because I think before we've been proving n to the whatever function to the n plus 1. Normally that's how we've been doing. But I see you started with before n minus 1, and then now you want to prove s to the n.
Okay, that's a valid point. Usually in the induction proof we've been going from n to n plus 1, but also in recursion we said that the easiest way to do it, since we were going to use this definition, the easiest way would be to make the closed form for this and closed form for that, and then combine them to get the closed form for Sn. Because this is a definition that we already have, and we need to use it for our proof. So that's why we don't go from n to n plus 1. For one thing, our recursion has to look back two things, right? So even if we wanted to prove something for n plus 1, we would have to use n and n minus 1, because we'd need to use this formula. I think it's easier to write these two and prove this one. Also, plugging in n plus 1 and looking for that is kind of harder than just n.
Yeah, gotcha.
So this is the method that I always use. But as long as there are three consecutive things, it's fine. As long as they match up some version of this formula, that's fine. Because this formula can be changed. I could put Sn plus 1 in here, and that would be Sn for this term, and that would be Sn minus 1 there. So as long as these match up with some version of this, it's okay. Because you're going to use your recursive formula in order to put the assumption in for Sn. So let's do that. That's going to be 4. I'm going to factor the 4 out of both of them. So it's going to be 4 times the first one minus that one. So 2 to the n minus 1 times 2.5 n minus 1 minus 2 to the n minus 2 times 2.5 times n minus 2. I'm going to factor a 2 to the n minus 2 out of both of these. Remember that I think in the last class or the one before that I told you that factoring was your friend. Okay, when you factor things, you don't have to find stuff in common anymore because you've already factored them out. So let me go ahead and factor out 2 to the n minus 2. The reason why I do that is because these two things, this is the smaller number, 2 to the n minus 2 is smaller, so I can factor that one out. I can also factor out a 2.5 if I want to, which I'm going to also do. So I'm going to go ahead and do 4 times 2.5 is 10, right?
It's 5.
4 times 2.5. So I'm going to use this 4 and the 2.5, I'm going to put 10. So that's going to be a little easier. And then I'm going to factor 2 to the n minus 2 out. So this one's going to be 2. If I factor a 2 to the n minus 2 out of 2 to the n minus 1, I have 1 2 left over because I subtract the powers. So that's 2. I already factored out the 2.5, so I have n minus 1 left. The second one, I have 1 left because I factored out 2 to the n minus 2. I factored out the 2.5. I have n minus 2 left there. So now I don't have any more halves to mess me up if I factor them out. Now this 10 has a 2 in it. It's 2 times 5, right? So I could go ahead and take that 10 and multiply it. I actually should have left the 2.5 because my final answer has that. So this is 2.5 times 2 to the 2. That's a times, and that's a point. Sorry about that. 2 to the n minus 2 there. And then I have 2n minus 2 on the inside, minus n plus 2. Looks pretty good so far. My last step is going to be...
What did you just do there?
Well,
You have 10. You have 10. Is that equal to 2.5?
It's 2.5 times 4. Remember I factored out the 2.5 and I multiplied by 4? That's parentheses there.
Okay.
I just changed the 4 into 2 squared because I realized that I had a 2.5 in here.
Okay.
And I need to have that. That's why we write our proof statement, because we know what we're proving if we write it. So these two multiply, 2 to the 2 and 2 to the n minus 2 multiply and give me 2 to the n, right? Because I add the powers. There's my 2.5, and my 2's cancel over here. And 2 to the n minus n just gives me 1n, right? So that gives me what I want, which is 2 to the n times 2.5n. I know I skipped over a lot of that, but you should be able to look at this later and be able to tell what they are if you take a little bit of time. But the algebra wasn't the most important thing. The most important thing was getting the assume and prove right, and then setting it up with the recursive definition and plugging in. The algebra, you can, even if you miss it, the most you would ever miss is 20% of the problem. For not doing the rest after that plug-in, that's 20% of the problem, which is 2 points usually, right? So if you get up to here, this is the hardest part, setting it up. and plugging in the right thing is the hardest part. And I want you to be able to do that. Because once you can get that far, someone can help you with the algebra. But someone who never had this class wouldn't be able to tell you what to do up to this point. The rest of this is any person that can keep their math straight can eventually get it, right? Okay. So that was a review of how we do induction proofs for recursion. So let me get my notes right quick.
The whole thing, that whole thing that we just did.
That whole thing was we found the closed form first, and then we proved it true by induction.
So the closed form was 2 to the n times 2.5n.
And that's what we just proved. When we prove something by induction, we have to, and it's a recursive definition to start with, and we're proving closed form, we have to prove that the closed form sort of propagates through the recursion, and that's why we start with the recursion when we do the proof. Because the formula has to make sure that the powers keep going. So whenever I use the recursive formula, it has to sort of preserve the way the closed form works, and that's why we did the induction proof using the recursion. Anyway, we don't know anything else about the formula except the recursion, so we have to use that. Okay, I'll believe you since you're the teacher. Okay, so we have some, in your packet 4, you have an exam review sheet. And there are some things on here that are not going to be on your test. So that's not very big. Let me make it bigger. And then focus it. There we go. That looks pretty good. Is that okay for you guys? All right. So there's going to be predicate calculus on the test. We're going to use truth tables to prove propositions for all and there exists. We already did a small one on that test, so we won't do that kind. Whatever we did on the last test won't be on this test. We used De Morgan's to change a proposition from one kind of proposition into another. And you'll have to fill in truth tables with propositions. In sets, we're going to remember the operators, which were what? Union, intersection, minus, or difference, right? Symmetric difference is exclusive or. That's what symmetric difference is called. And I think that's it. Complement. Don't forget complement because it's also written as a bar. Complement is the opposite of a set, so the stuff that's not in the set. So don't forget that one. People forget that a lot. Okay, we're also going to do power sets. I'll do a review of this next week. I just want you to have an idea right now so you can do some studying. We're going to do some set theory proofs. So you had all this on your homework. I'm just pointing these out. So if you look over homeworks 4 through 6, that's what's going to be on this test. Everything on homeworks 4 through 6. So we're going to do some induction proofs. I don't care if you know the difference between first and second principle. In first principle, we go from n to n plus 1. In second principle, we use all the values from 1 to n to prove n plus 1. That's the difference between those two. The first principle says you can assume n is true and then prove the next one. The second principle says you assume that the first group of them is true and prove the next one. And we're sort of using a version of the second principle when we do the recursion proofs because we use more than one assume step.
Does either way work?
Each problem, the structure of the problem that you're trying to prove tells you which one that it requires. So if you have to know that the first n things are true, you're going to have to use them in order to do the proof. If you don't have to use them, don't use them. Okay. So it's whatever the problem is that tells you whether you need it or not. Okay, so we're also going to have recursion on the test. So recursion's on there. You want to be able to get a recursion. We just did the cheat method for getting a recursion. You can also get them from a table. Also from plugging in the recursion definition again and again. We did that too, sort of unrolling, like the computer does. If I want to find f of 5, it says, oh, do this to f of 4, and then it figures out f of 4 and figures out f of 3 and plugs those in. So you could do that too. Generating closed form from recursive form, we just did a definition of that with linear homogeneous. Some of those you're going to have to guess. because you can't always use the linear homogeneous formula. You're going to have to get recursive form from closed form and proving that closed form is equal to recursive form. BigO will not be on the test. I just wanted to point that out since it's in the review pack. It's just it's on test 3. Any questions?
How much old stuff?
How much old stuff?
In terms of like from test 1.
There won't be anything from test 1. Each test covers a few homeworks. So the first test was homeworks 1 through 3. The next test is homeworks 4 through 6. The next test is 7 and 8. And the last test is 9 and 10. So if you look at last year's exams covered BigO, and they also had harder induction proofs. So the in-class test, the take-home, is harder than I will give you in class. So I'll give you easier ones than are on the take-home. Okay, so let's talk about BigO some more. We talked about big theta, big omega, and BigO last time. Let's talk about those things some more. Okay. Ooh, I zoomed. I'm not in focus anymore. Okay. So let's remember what BigO is. What is BigO?
Everything, like a function, it includes everything of a function and lower.
Right. So if I say that, if I say that a function g is in big O of f, that means that g is less than or equal to c times f. Right? So that means that f is an upper bound for g. So if I have two functions, one that looks like this and one that looks like this, do you think that one is big O of the other?
No.
No. Well, I don't know. Is one over time?
It is.
Yeah.
It is, because all I have to do is multiply one by a value and just move it up. Right? Mm-hmm. So they wouldn't be if they look different. So let me show you some pictures. So these are big theta of each other because they're approximately the same size, because I could draw lines around both of them and they're about the same size.
You asked, is one big O of the other?
They are. They're big O of each other. So f, say this is f and this is g, f is in big O of g because all I would have to do is multiply g by something and make it higher. And g is also in big O of f because they're approximately the same size. So if you look at a graph and you think, oh, they're about the same, sometimes one's a little smaller than the other, they're the same big theta of each other because they're about the same growth rate. Right? So they might wiggle and be different, but they're approximately the same size because I can bound them both by this line, these lines here. Or if I could bound them both by the same, like lines around a curve, they would be the same growth rate.
I mean, it looks like you'd have to shift it over to the left or to the right a little bit instead of up or down.
If I'm talking about bigger, that's on the y-axis, this way. So if I move an entire function up this way, that's what multiplying does. It doesn't move it totally. It adds. I could just add 20 to one of them and make it higher than the other, right? Whatever this is, I can just add this value to one of those functions and just knock it right up.
Okay.
So they're about the same growth rate. Like one of them's not way bigger than the other, right? So if you can look at the graph and say, oh, they're almost the same, or you don't really care what the difference is, then you know they're the same big theta. Okay, if I have two functions, like this, which one's bigger?
F.
F is bigger because out at infinity, F is going to be way higher. It's actually already higher right here. If I pick one value of x, here F is bigger. And from now on, it's going to be bigger unless it does something funny later. So G is in big O of F, because F is the upper bound for G.
That's clear.
And in this case, F is in big omega of G. They're sort of opposites. Okay, so these are lower bounds. So big omega is lower bounds. And since G is a lower bound for F, because we know F is usually bigger, then it's in big omega. And these are upper bounds. So F is an upper bound for G. G, in this case, G is a lower bound for F. So they're not in the same, they're not big theta of each other, right? So F is not in big theta of G. Because they're not the same size at all. They don't grow at the same rate whatsoever. I wouldn't say it was equivalent to run the algorithm for G and the algorithm for F, and I would be the same amount of time within a constant. No way. So that's the whole point of these, is so I can look at these things and tell which one I would want to run. So there's a trade-off with big O, right? If something, say something's like 500 times some, say I'm comparing like, if I was comparing 500 log of n and n, at first this might seem too slow, right? If I was plugging in 1 and 10 and whatever, this will be a lot faster. So you have to examine, if you're really going to use this stuff, you have to examine your inputs, see how many you're going to usually use. If you're usually going to use less than 20 things, you might want to run this linear algorithm. But when we're talking about big O, we're worried about large numbers of inputs. And that's why we talk about it in the first place, is because, you know, if it's a matter of 10 or 20 things, who cares which algorithm you use? You could use a factorial algorithm, right? If you're going to do things up to 20, it doesn't matter if it takes 120 operations, because 120 operations is like that on any of your computers. So 120 is 5 factorial. So, you know, if you're only going to do 5 inputs or something, I mean, factorials grow really fast, right? Because then 6 times that is the next one, and then 7 times that. So they grow very, very fast. So typically you want something smaller than a factorial algorithm. But there's problems. Just to give you a little introduction, one of the reasons why we have big O is there are problems that have no known polynomial runtime algorithm. And they're called NP hard. So P is called polynomial time algorithms. And NP is non-polynomial. So an example of a non-polynomial problem is anything that would take a factorial amount of time, because that's definitely not a polynomial, or anything that takes an exponential amount of time. So even listing a power set is not a polynomial time algorithm, right? Because a power set has 2 to the n elements. So if I have to list, if I give you an n and you say, give me the power set of a set with n elements, I have to list 2 to the n outputs, right? So my time is 2 to the n. Doesn't matter what I do, even if I'm really clever, I have to print them out. I have to print out 2 to the n things. So that's the amount of time it takes. So some examples of these functions are 2 to the n factorial. So let me give you a classic NP problem, since we're talking about it, the traveling salesman problem.
Is that 2n or 2 to the power of n?
2 to the power.
2 to the power of n. 2n is a polynomial. The traveling salesman problem is that you have several cities you want to go to and make sales. But of course you don't want to go to any city more than once because people would recognize you at the door and close the door, right? So, and you also don't want to pay expenses to get back and forth between cities that you've already gone to. So what you'd like to do is, this is where you live, right? This is your little house over here. And you want to go to all those cities and get back to home without going to any city twice. Okay, and there's certain roads and things connecting these that you can use. You have to connect that somewhere. So the traveling salesman problem is NP hard, because given any arrangement of these cities and any lines between them, you know, any roads connecting them, there's no algorithm that'll tell me the best solution, or even whether there's a solution that'll get me to all the cities without visiting any of them twice and get me back home. There's no known algorithm that isn't factorial. So the factorial algorithm, what do you think it might be? How do you think you might solve this problem?
I'll take a route out.
You could just try some routes, right?
Or remove a change route, I guess.
Remove what?
I was going to say remove a route, but then that would leave you.
You can just
You'd
try
have
routes
to-
and see if they work, right?
Right, you just
So what you could
exactly.
do is just list the vertices. These are called vertices. We're going to do graph theory later, so you don't have to write this down. But just while I'm talking right here, these are nodes or vertices or cities. So you could list the cities in order and just see if you could actually go that way. So I could just start with listing A, B, C, D, E, and then back to A. Does that work? No. This is characteristic of an NP problem. NP hard problems, it's really easy to look at a possible solution and say, that's bad. Or to say, yes, that's a good one. So that was a bad solution. Let's try another one.
Excuse me, why did you say it's bad? I thought you'd leave.
There's no line from A to B.
Oh, there's no
I can't
line.
go from A to B. So it's not a possible solution. It was just, I just listed a random list of the
Random
cities.
list, okay.
It was random.
And those lines are just random? The lines you
No,
draw?
no, no. These are given. These are given
Oh,
in the
that's
problem.
given. Okay.
Yeah. So if you had any set of cities, and say you had to take an airplane in between the cities, you would be given which ones you could fly between, right? So you don't get to set that. What you have to do is find how to go to all the cities and get back home, and not go to any city twice if you don't have to.
Can you make a turn?
Yeah, I was getting ready to ask that.
Take two different, make a right turn at one of those?
Can you make a right turn? If you go to it, that's considered visiting the city. So you can't. Oh, you mean like at these intersections?
Yeah, can you?
No, those are just lines that connect the dots.
So they're overpasses.
Yeah, they're
There's no way you
overpasses.
can
There's
do
little
that.
overpasses here.
What layer? So those allowed?
You have to end up back at A.
Right. In this particular problem, there's not a solution
Right.
for this one. Okay? I can see it by looking at it, but there's no algorithm that can just look at any graph and say whether there is or not, which is kind of neat. So it's an open question of whether you can actually get a polynomial time algorithm for this. So let me emphasize that again. Like, okay, before I do that, let me show you the way I would do this. I would list all the orderings of the cities. One of the possible ways to figure out this problem is list all the orderings and check and see if any of them work. Right?
Which would technically be a variable
A lot of
named factorial.
Right, so this is a factorial, right? Because I have 5 nodes and all the orderings of them would be 5 factorial. And we're going to do that counting problem later. But there's 5 factorial orderings, which is 120. But in an even larger graph, it's even more, right? So then you would check all of them. So this is the easiest non-polynomial algorithm for this problem that'll solve it for any graph. You can say yes or no after you list all of those and check them. Make sense? Good. So that's a polynomial time, non-polynomial. So that's an n factorial problem. But let me just tell you, no one knows if p equals np. We just might not be smart enough to figure out that problem in a polynomial amount of time. There might be somebody who could do it. Okay? So we haven't proved that yet. You can prove things are in NP if you can show that so if I want to prove algorithm A is in NP, if I can show that A can be solved using some algorithm B that's already in NP. So say I had another problem that was a lot like the traveling salesman problem. If I could just figure out how to solve my problem with the traveling salesman problem, then I would be showing that it was in NP. So that's how people grow that set. So if you want to prove to people that you have a hard problem that's going to take a lot of time to solve, that you can't really do efficiently, you would prove to them that it was NP. And you would say, nobody knows how to make a really good algorithm for this. I'm going to prove it's in NP. And then if you got a good solution, everybody would be happy because you got a solution that wasn't factorial. It might not be perfect, but a heuristic solution. So what people normally do for problems in NP, they write heuristics. And what does the word heuristic mean?
Kind of like, I guess, like an approximation.
Right. So what you do is heuristic means rule. That's what heuristic means.
Rule of thumb.
Right. So you use something like a rule of thumb or a good guess. Right? So these are non-optimal, which means you may not find the very best solution, but you'll probably find a good enough solution. And you often can write polynomial heuristic algorithms. And that's what people often do. And so that's a huge area in computer science, is figuring out good heuristics for problems that are NP hard. And it's also really interesting. I just read some presentation abstracts today for a presentation that's going to be on Friday afternoon by some grad students. And one of the problems is that somebody has a problem that's NP hard to solve, and they come up with some algorithms to make it easier to solve with the particular problem that they're doing. So it's lots of research and that kind of stuff. Okay, so let's get back to BigO, but this was just to point out that growth of functions is really, really important in computer science. So if you've got a factorial problem, that's not good. So you want to either figure out how to do it without factorials or figure out some heuristic that will solve the problem for you. So if you have lots of inputs, you're not going to be able to do it in your lifetime. Okay. Factorials grow that fast.
What time is that presentation, Friday? I'll be there.
The presentation Friday is at 10 a.m. in EGRC. It's open to the public, EGRC room 246. And it's by CSC grad students. And it's a competition. There'll be 3 presentations. And it's sponsored by the GSA, Grad Student Association. And there's going to be one on scheduling, parallel scheduling. One on networks, optical networks.
So is that parallel one, like parallel processing?
Yes. And the other one is on an intelligent tutoring system. So there's 3 presentations on Friday if you want to go. I'll be there. Yes?
When you just said that the other problem, that the factorial problems, that you wouldn't be able to solve that in your lifetime?
Because you have lots of inputs.
Right, but isn't that, to me, that seems like that's the point of the computer, is to be able to do that stuff for you.
That's the point, is that if you have a factorial algorithm and you put in like, a bazillion inputs and you have a factorial problem, if you want to calculate out how long it would take, it would be like 1,000 years for some of those problems. You don't want to wait 1,000 years.
Computers that can do
Even
billions
with
of calculations
computers,
a second.
no matter how fast you get it, I can always give you a bigger problem.
Okay.
As a matter of fact, one of my research problems that I did a few years ago was so big I had to do it was a recursive algorithm, and it was took a long time. I had to wait days for the output to come out.
What kind of a problem would you want to solve for something like that?
Traveling salesman problem.
Wasn't the human genome problem really, really huge, and they had to get people to use their home computers overnight?
Yeah,
to
lots
solve
of
it?
used 20
projects have
computers
got
for 4 years.
20 computers for 4 years.
Yeah.
So the Human Genome Project right? There's lots of projects that people are doing. So I had 4 computers for 20 years? No,
Other way around.
20 computers for 4 years.
So I guess what you're saying is that other problem that you gave us, there was no solution to that, right?
Right.
But if you had, like for the post office, you have 500,000 routes that the post guy needs to take. Solving a problem like that so he doesn't have to go down the same street twice
Well,
is...
in that case, all the houses are connected by streets. If everything's all connected, you can just pick any way you want to go.
Yeah, but without going down the same road twice.
Sure.
You can pick, if you have, these things are all connected every way, I can list any ordering. If all of them are all connected, this is called a complete graph. If everything's connected to everything else.
No, I don't mean like that. I mean, like, you know how some roads aren't connected to others.
For the most part, most roads are connected to other ones, so they don't have to worry about that problem. And besides, if there's a short road that's not connected to too many roads, you don't mind if you drive down it twice, right? And nobody lives on highways.
Seeing what kind of a problem or what kind of problem you'd want to solve with that. I mean, because like you said, some of that can't be solved. And is that what you're trying to prove?
You can use heuristics to solve problems that would take your whole lifetime to solve. And that's what we usually do. We just assume we can't get the very best solution. We'll just try to get a decent solution.
Okay.
Okay? And a lot of times you'll have classes of problems that you can solve in your lifetime as long as you put some constraints. So this NP hard problem doesn't mean there's no situations where I can find an answer. It means that if I can't sit there with my magic globe and anytime anybody gives me a graph, I can solve it in a few seconds.
Okay. So
But if I could say, oh, the graph has to have this many roads and this many connections and stuff like that, then I can solve it in a smaller amount of time.
Well, when you say solved, you don't mean like mathematically solved, right?
Yes, I do. I mean finding the best solution.
But a best solution for me might not be the same as his. Or are
When
they
you
going to
give
be
a
the
problem, hang on.
same? Okay.
This is not stuff that's going to be on your homework, so we're not going to spend any more time on this. But when you're given a problem, the problem specifies what the solution should be. You don't get to pick what is my best solution, what is her best solution. Okay? Whoever makes up the problem says this is what the solution should look like, and you have to find it for me. That's what computer science people's jobs are. You don't get to say this is the best solution.
Okay, well, that's
You
the
have
part
to
I missed,
mathematically prove that you have the best solution.
Okay, you're given this. Okay.
Right. You know what the solution looks like. Somebody can look at the solution and tell if it's right or not.
Okay.
Okay, so let's get back to BigO. So that's why growth of functions is important, because we have to compare growth of functions, and it's very important to know how long your algorithms take to run. Okay, so let's just do some more example problems. So again, let's try. Let's compare n log n and log of n factorial. Let's figure out which one's bigger. Does anyone have a guess?
Log of n factorial.
And log of
Okay, I want to have a vote. Who says log of n factorial is bigger? Okay, that's 3 people. Who says n log n is bigger? Oh, that's like 8 people. Okay, you win. This one's bigger. Why is that? Because n log n is equal to log of n to the n. That's the difference between the people who voted for this one and this one. If you know and understand logs, you will know that this is log of n to the n. And if you compare n to the n and n factorial, which one's bigger? N to the n is bigger. So let's do this proof to get practice with doing proofs that have logs and factorials in them. Even though I could, this is a very cheap thing to do, but you can do this, right? And raise both sides to the power of 2. Right? And then that would be proving that n to the n is greater than n factorial. Perfectly legal move. And then you could do this proof, and that would prove that one. Okay, but that means you still have to do an induction proof. So you can't just do this and go, ha-ha, I'm done. Okay? You still have to do a proof by induction. If I tell you to do one, you need to do one. Okay, so let's do this problem, the n log n one, because you're going to have log ones that you won't be able to do that with. So let's start with the basis. Is n equal 1 going to work? Let's put an equal in there. So 1 times 0 is greater or equal to log of 1. That's equal to 0. So 0 is greater or equal to 0 works. I write my assume statement, just write out what you want to prove. This is one that goes n to n plus 1 because this is not a recursion. Numbers grow. They go from n to n plus 1. That's how they grow, so that's how I do my proof. When I have a recursion, they grow from previous steps to the next ones, and that's how I have to do my proof. So however something grows is how you have to do the proof. So here I have to prove that n plus 1 times log of n plus 1 is greater or equal to log of n plus 1 factorial. So now I've done my setup.
Where did the n plus 1, the leading n plus 1 come in the proof?
That came because I had an n there.
Sleep.
That's all right. Okay, so this is what I want to prove. Now I think the right-hand side is going to be the side to work with. And I know that messes you guys up because I normally did left-hand side. How do I convert this to a left-hand side? Swap them
Sign.
and flip the less than or equal to. So let's write it again.
Why did you flip them?
So we'd work with the left-hand side because that's what I got you guys used to.
Right, but is there a reason why you wanted to work with the left side and not the right?
No. I can work with the right-hand side just fine, but y'all aren't used to that, so I'm going to work with the left-hand side.
Okay.
All right, so I start with the left-hand side of what I want to prove. And you'll see in just a second why I wanted to work with this, the log of the factorial, instead of this. Because the log of a sum I can't break down into anything else. But a log of a product I can break into a sum, right? Log of AB is log of A plus log of B. So if I start out with log of n plus 1 factorial, n plus 1 factorial can be written as what?
Log of n plus log of...
N factorial times n plus 1. Let's go ahead and do it inside the parentheses. Right? N plus 1 factorial is n factorial times n plus 1. Then I can break those up because that's the log of a product. That's log of n factorial plus log of n plus 1. Now this looks like the left-hand side of what I had, right, of my assume statement. So now I'll do my substitution, but I have to use a less than or equal to instead of an equal sign. Substitute in n log n plus log of n plus 1. Now at this point, I have to do my little magic step, and what's that? The magic step is saying that I want this to be less than the right-hand side of what I wanted to prove. So I'm going to write want n log n plus log of n plus 1 to be less than or equal to. So I don't know if this is true or not. Sometimes I put a little question mark over the less than or equal to, so I know that I haven't proved it yet. Everything else that I've written down so far is proved. So I'd like that to be true because then I'd be done with my proof, right? Because I just proved that the left-hand side is less than this intermediate step here. And then if this intermediate step is less than my final step, then I'll be great. I'll be done. So let's see if we can prove this. If I multiply out on the right-hand side, so I'll put a question mark over this less than or equal to since I'm not sure yet, n log of n plus 1 plus log of n plus 1. I just multiply out that n plus 1 on the right. Then I can subtract log of n plus 1 from both sides. And then I'm left with n log n. Still not sure yet if that's less than or equal to n times log of n plus 1. Okay? If you can look at this and assure to yourself that it's true, then you're done. If not, just keep working. You divide both sides by n. Is log of n less than log of n plus 1? If you're still not sure, raise both sides to 2, power of 2. That gives you n is less than or equal to n plus 1, and that's true. Right, so I divided out the n's, and then I took the exponent of both sides. Said 2 to the power log n, 2 to the power log of n plus 1. And then the logs go away and the 2's go away. So that's true, so therefore these are all true. So then log of n plus 1 factorial is less than or equal to, where is it? Here. So I'll write it again on the next sheet. So therefore, I'll just finish. Hang on, I'll go back. So this was my final goal. That's what I have. So from here, I broke this down because it was a product. Broke it down, got it to a sum. That was from my assumed statement. I did a replacement with the right-hand side. Then I wanted this stuff, which is intermediate, to be less than what I wanted to prove. If it was, I'm pretty happy. So we did end up with a proof that that was true. So therefore, so I'll just say A was less than B was less than C. So therefore A is less than C, right? So we used hypothetical syllogism, kind of, to get this. Question?
On that want part, is it part of the formula that we always want it less than what we want to prove?
Absolutely. We want that less than or equal to, so we want to get that.
Is that what you meant by changing it to a left-hand side inequality?
Yeah,
No.
all she did was she just took this equation right there
Okay.
and flipped it, mirrored it. So you got to do the whole thing. You got to flip the whole. See, this goes there, this goes there.
I was using just my basic, regular induction stuff. Assume, prove, start with the left-hand side of what I was proving. That's why I changed the equation, because I would have started with the right-hand side, which is perfectly legal to start with the right and get the left-hand side. It's just you guys are used to the left-hand side. If I had started with these, I wouldn't have got very far, because I couldn't break them up and get one in terms of the other. And that's why I started with this side. So factorials are easier to break up and get in terms of each other than logs of some other number. Okay? If I would have started with this side, I would have had to raise both sides to the power of 2. Right? Because I couldn't get this log in terms of that log. I might get one that was bigger or something, but that's even trickier to do. Okay, let's keep going. Let's go back and do one thing that I didn't do. Actually, let's see. So we just did this was a big O proof. So we just proved that n log n is greater than or equal to log of n factorial. So we really just proved that log of n factorial is in big O n log n. So if I prove an inequality, I'm actually also proving a big O. So that was a proof that log of n factorial is in big O of n log n. Okay, they're not the same big theta because n to the n and n factorial are just, they grow similarly, but n to the n is so much bigger than n factorial still that they're not the same growth rate. Okay, so what was my order of functions again? I had 1 log n, n squared, n cubed, and so on. We had 2 to the n, and we had n to the n, and we have n factorial in between there. So where does n log n go in this table?
Log n.
Number 2.
N log n goes right there. Where does log of n factorial go in?
The factorial.
Well, we just said that log of n factorial is in big O, so it actually has to go on this side,
yeah.
right? It's bigger than n, though.
Yeah.
So it goes in here. That's the only tricky one. You could plug in some values, though, to find out that this is bigger than n, but it's smaller than n squared. And you know it's smaller than n log n. Okay, so these are the kinds of things you can use to figure out the big O. Because on your test, you're usually going to have to prove one of these things, and then I'm going to make you list these functions when you take your third test. I'm going to make you list them in order. I do that every year. I'm going to do it again.
Wow. Scary.
How many points is that worth?
How many points is it worth? Probably 7.
Start memorizing.
Start memorizing. You can figure this out again and again. Okay, let's see. The next thing I wanted to do was go back and do a recursive definition of a set. So let's define a set recursively. Let's say I have 0, 0 in my set. So T is going to be my set. And if AB is in T, then A plus 1B is in T, A plus 1B plus 1 is in T, and A plus 1B plus 2 is in T. And suppose I want to prove some property of T, of all the points in T. This is an infinite set, right? Because if I start with 0, 0 and I just add things on every time, it's an infinite set. Because I can add any number of times recursively. I can use rule 2 over and over and over again. So give me some points that are in this set.
1, 1.
Well, what's the first point in there?
1, 0.
0, 0.
0, 0. Okay, always start with the one that's given to you. So these things, I'm just listing some things in T. I'm not going to list the whole thing because it's infinite. I can't finish that. So if 0, 0 is in there, then what does the rule tell me? It says if 0, 0 is in T, then
1, 0.
0.
1, 0 is in there. 1, 1, and 1, 2 are all in there. And then if 1, 0 is in there, then I can use this rule to say that 2, 0 is also in there, and 2, 1, and 2, 2. And I can plug in 1, 1. So any of the points that I've got listed so far, I could plug into the rule and get some more sets points. So if I plug in 1, 1, that gives me 2, 1, which I already have in there, but the rule gives it to me again. It wouldn't be counted twice in the cardinality, right?
Right.
It would just be counted once. So it would give me 2, 1, and 2, 2, which both of those were already in there, but it would also give me 2, 3. So that was using 1, 1. This was using 1, 0. So these grow. Like every point gives you 3 other points. And they might overlap some. But if I wanted to say I wanted to prove something's true for all of the elements of this set, what would I use to do that? Induction. Your favorite thing. So let's say that I wanted to prove for all points A, B in T that 2A is greater or equal to B. That's what I want to prove. Does it look like that's going to be true? If you look at all these points, that's true, right? Because the most the right-hand side is bigger than this one is 1. So it makes sense that twice the first one ought to always be bigger than the second one. But let's prove it. So we have to start with a basis, right? So we're going to prove that 2A is greater or equal to B for all AB in the set T. So our basis is we have to show that for 0, 0, 2 times 0 is greater or equal to 0. 0 is greater or equal to 0 is true, so that's going to be true. Now, in order to structure our induction, it has to be structured the same way our recursion is, right? So our recursion has one step that we assume and then grows 3. So our assumed statement is going to have one element, and our prove is going to have three statements. So our assume says that if AB is NT, then 2A is greater or equal to B. We want to prove for all of those recursively defined set points that twice the first element is bigger than the second one, bigger than or equal to the second one. So I have three statements to prove now because from one thing I grew three. So when we did the linear homogeneous recursions, we had from two things we grew one. So we had two assumes to prove one thing. Now we have one thing to prove three assumes. Sorry, three proofs. One assumed to prove three items. So I have to prove these three statements. So I already know that 2A is greater or equal to B. So this is my given. And these three came from AB. So I know AB was NT, and since that was NT, these three were NT. So this was a point I got, and these are points I know are in there because of the recursive definition. And now I just have to, I know this is true, now I just have to prove these three things. That's what I don't know.
You already know that if 2A is greater than B, 2A plus 1 would certainly be greater than B.
That's right. So if 2A is greater than B, that implies that 2A plus 2 is greater than or equal to B, right? And that's the same as 2 times A plus 1 is greater than or equal to B.
Right.
So I've proved the first one, right? So that's the first one. So I have 3. Let's prove the second one. If I have 2A is greater or equal to B, I could add
If you add 1 to each side,
one to both
you're
sides.
just doing the same thing to each side, so you got to know that's true.
2A plus 1 is bigger than B plus 1, right? And if that's true, then certainly 2A plus 2 is bigger than B plus 1. Right? And that's the second statement I needed to prove.
What?
Because that's the same as 2 times A plus 1 is greater or equal to B plus 1. That's number 2. And the third one is actually just adding 2 to both sides. Right? So that's a one-liner. So if I have 2A is greater or equal to B, then certainly 2A plus 2 is greater or equal to B plus 2. And that means that 2 times A plus 1 is greater or equal to B plus 2. So this is the third one. So this was an easy proof, but it was to show you the structure of what happens when you have a recursive definition. You have to grow the induction the very same way that you grow the recursion. So the way
stands true for that rule stands true for anything. Anytime you do recursion, that you have a recursion definition, you're going to have the same amount of proof statements that you have in the definition
Right.
statement.
So the structure of induction is exactly the same as recursion all the time. So they go hand in hand. The two things go together. So let me just draw you a picture of how that works. So the thing we just said was a definition that grew us a little tree, kind of. That's how I like to think of this. So think of yourself making a little garden, and every time it grows new sprouts, it grows 3 of them, everywhere evenly. And that's what our recursive definition just told us. We had 0, 0, and then it gave us 3 new things. So if I wanted something to be true for the whole tree, I have to prove that if I'm at some node, then going up each of the 3 branches is going to be true. That's why we had 3 proof statements. With our regular recursion, like with our recursion that had something like S of n equals S of n minus 1 plus S of n minus 2, which is which recursion, by the way? Fibonacci if S of 0 equals 0 and S of 1 equals 1, right? That just happens to be the name of it because a guy named Fibonacci found it. Okay, that's why it's called Fibonacci. There's nothing else about it that makes it hard. Okay, so in that particular instance, we take the current element was made from two previous, right? So it goes like that. So when we do our proof, we're going up this way, so we have to assume these work to show that that one works.
So the two that you just circled are kind of considered N. You're trying to prove it.
Right. It's sort of like I'm coming from this level and proving that level. Because those are previously known things, I'm going to the unknown thing. Okay? Good. All right. Okay, just for an exercise for the last minute or two, let's just find some big O of some functions, just to have practice for that because it's on your next homework, which is going to be in a while because you have a test next week, so your next homework's not due till the following week. So you need some practice on this because next class, I'm going to go right on. Okay, I'll do some test review, but I'm also going to move on to some new stuff.
Is this the induction stuff that we just did on the test, on the second test?
All of induction is on the test,
Okay,
and
so-
all of recursion is on the test, but big O it's not. So I'm not going to make you do any big O, and I probably, if you do have a less than or equal to proof, it won't be a hard one. Okay, so you'll have induction and recursion, but I won't have anything that's really related to big O. Okay, so let's do some practice. N to the 2 to the N plus N.
So that would mean that it's going to be, the problem would be like 1 is less than 2, because that's pretty easy for me.
Oh, it must be the end of the day.
I get better with time.
Okay, so let's find the big O of this function. So our big O rules tell us to look for the largest term in a sum, right? So we look for the largest term in a sum, and then we replace all the other terms with that. So what's the largest term here?
N to the 2 to the N.
N to the 2 to the N. Was that clear to everybody? That's because if all of these are the same, I can just compare the powers to see which one's biggest. We know that log of n factorial is bigger than 500n because we just talked about that. Because we figured out that log of n factorial grows a little faster than n. But 2 to the n is way huger, so this is the big one. So all of these, that would be the same as replacing all of those with n to the 2 to the n. So that's 3 times n times 2 to the n, n to the 2 to the n. So this is big O, n 2 to the n. And what is my minimum n here? I've got a log in there, so let's start it with 2. If I have logs in there, just start with 2, you'll be safe. Hopefully. You could go back and check it, but 2 probably works.
So you shortcutted, you don't have to write it down.
I
but you
shortcutted replacing each of those.
Replacing each of those with
Yeah.
n squared.
Since there were
n
3
to the
terms.
2 to the n.
That's right. Since there were 3 terms, I went ahead and replaced all of them and did that. Okay, let's do another one. Holy cow, someone said. Okay, this is just for practice to find big O. If this happens to be something and you have to figure out how big it grows, you need to be able to do it. So we look at the sums. Again, we just do sums. That's all we have to deal with. So this first set, what's the big O of that? N squared.
N squared.
Assuming I wanted to get the constants, I would put 2n squared, right?
Yeah.
So because I would replace both of those with n squared. So that would be 2n squared. Later I'm going to drop all the constants at the end. Inside the log, let's do that sum. Which is bigger, n or n squared?
N squared.
N squared. So I'd replace this with 5n squared.
That's 8n squared.
So that would be 8n squared on the inside. And so far I've just needed n is greater or equal to 1, right? Sorry, I wrote that off the side. N greater or equal to 1 is what we've been using so far. And then on this last one, I have log of n plus 5, and what's the big O of that one? N, right?
N.
So I would put n plus 5n, that would be 6n on the inside there. Okay, which one of these two is bigger? N squared log of something or log of n?
N squared.
N squared.
So n squared.
This one's going to be bigger because n squared is a lot bigger than taking log of a log. Right? Log makes something a lot smaller than it originally was. So if I want to get rid of this constant, I actually have to separate them out. It's going to be ended up with log of 6, right? So if I wanted to be really technical, that's what I want to do. But right now I'm just going to drop the constants. I could just drop them, okay, to figure out what the big O is. So if someone just asks you what it is and they don't say prove it, this is going to be n squared log n plus log of n. And n squared, log of n squared is 2 times that log of n, right? So this is 2n squared log of n plus log of n. Which one's bigger, this one or this one? It's the first one, because 2n squared is bigger than log of log. So the big O, I would just say, is n squared log n. I could go back and find the constants if I wanted to. Just getting all these constants out of here. But just finding the bigger one is the most important thing. And then you can go back and prove it later. If we were really careful every step, that would have been a proof. Because then I would have taken this constant out and everything. But see y'all next time.